Welcome back, guys. So now we're talking about production functions. So what is a production function? It's basically a function or a function that shows the relationship between inputs and outputs. So how we denote it, it could be Q, which basically denotes the output. We assume for simplicity that you are producing a single output. And the production function is usually denoted by F. And then the inputs. Well, the inputs can be anything. But, in general, you need capital to produce an output. You need labor. So the capital can be measured by units, by numbers. And the labor can be measured by working hours. M can be, for example, raw materials and any other inputs which are not included in any one of, which are not covered by any of those three. Most of the times, however, for simplicity, we look at the case where there are two inputs, capital and labor. All right? So this is the two input case. Probably, some notions that you already know from intermediate micro is the marginal productivity. Well, the idea is the following. Very similar to marginal utility. The marginal productivity is basically additional units of outputs you can produce by using an infinitesimal or small units of increase in one of the inputs. So for example, if we're talking about marginal productivity of capital, so marginal productivity of capital, we basically mean if the production function is a differentiable function, it's the partial derivative with respect to the variable capital. So therefore, the marginal productivity of capital is del F del K. We normally assume that this is a positive parameter, a term. Well, why is that so? Well, it makes sense, right? The more input you use, the more output you can produce. And similarly, if we're talking about marginal productivity of labor, we denoted MPL. And again, it's the partial derivative of the production function with respect to labor. And we also assume that it's positive. Well, what about the second derivative of the production function with respect to capital and labor? I mean, what about del F square, del square F, I'm sorry, this would be a more correct notation. So del square F del K square and del square F del L square. So basically that means you are taking a second derivative of the production function with respect to capital. Well, is this positive or negative? Well, we usually assume negative for both capital and labor, and this basically implies that diminishing marginal productivity with respect to capital, and similarly diminishing marginal productivity with respect to labor. So in general, just diminishing marginal productivity. Well, what's the idea? Idea is the following. If you are using more input, capital or labor, you can produce more output. But the thing is, the amount of this increase as you increase your capital and labor is going to decrease. So mathematically, basically that means the production function is an increasing function of its inputs. So I'm going to draw for capital, but exactly or similar graph will be the case for labor. So if I increase the input capital, well, the quantity Q is going to increase. But what is the fashion of this increase? Is it increasing in a concave fashion? Is it increasing in a linear fashion? Is it increasing in a convex fashion? Well, what we usually assume is that it's increasing in a concave fashion. So that's where the second derivative plays an important role. So it's negative means the production function F capital labor is increasing as we increase capital, but you know what? After some point, the increase is not huge. So for example, when capital is very small relatively, the size of the sort of the marginal increase, that basically means the slope of the production function is very high. However, as you use more and more capital, well, the marginal productivity of capital becomes very, very small, almost sort of zero if it is completely horizontal. Well, what's the intuition behind this? So think of you have a factory, and in this factory, you can basically put a limited number of capital. Well, what is capital? I don't know. If for example, it's a call center, all right, let's suppose it's a call center, and so the one capital is, for example, a computer, all right? So how many computer and, computer desk and phone. So how many computer you can put in a limited sort of physical environment? 50, 60. So if you try to put more and more capital, basically you're squeezing all the workers very close to each other, and so probably you're going to be reducing the productivity. It's going to be too crowded environment, and so the working environment is not going to be as pleasant as it was, for example, when there were, I don't know, much less desks and chairs and computers. So probably you get the idea. Is like more capital. Yes, it produces more more input. Yes, produces more output. But the thing is, the marginal, the additional output you can produce from an additional input you're using is not going to be as great as it was when the level of capital or the level of input wasn't that high. So that's the idea of diminishing marginal productivity. So obviously you can also define the idea of average productivity. Average productivity of labor, for example. So what is it? Well, simple. The total output level when you use K level of capital and L level of labor divided by the unit of labor you're using. So basically what you're doing is, what is the average product that you're producing for each unit of labor you use. All right, so that's the idea. Well, similarly, you can define the average productivity of capital. And again, it's just your total product divided by the total capital input you're using. All right, so it's the average quantity, average output per a unit of capital you're using. All right, this is what you are measuring. Well, what is next? Very similar to the idea of indirect utility function. Indifference curves. We are now going to talk about level curves for production function. Well, why do we need the level curves for production function? Well, because you'll see later when we solve the optimization problem for producer, which is about minimizing the cost to produce a certain level of output, you need a level curve for the production function. So I'm going to talk about a simpler case where the production function is a function of two inputs, capital and labor, but the idea can easily be extended to more than two input case. And so what we can draw the level curve of I'm going to denote it by IQ0. So what I would like to know is that how much input, capital and labor, or how much input, so what are the input combinations that I need to use in order to produce exactly Q0 units of output. All right, so that's what this set is. So it's basically capital and labor, which is in R square, plus, right? We usually assume that you don't really use negative amount of inputs. It doesn't make sense, but obviously you can use zero amount of inputs, such that f of KL equals Q0. I don't want to produce more than Q0 or less than Q0, but I want to produce exactly Q0. So the question is, what are the input combinations, K and L, that I need to use to produce Q0 amount of output? So here the level is Q0, it's a real number, and so this is the level set for the production function F for the level of Q0. Or, briefly, we just call this Isoquant. Isoquant curve for the production function F. Well, so the idea is very similar to indifference curves. We're going to talk about different examples, but if, for example, your production function is Cobb-Douglas, something like k to the power 1/2, L to the power 1/2, then the isoquant, where do we draw it? Well, we draw it in a two-dimensional space where the first input usually, the horizontal axis is usually the first input, which is capital, and the second axis or the vertical axis is the second input, labor. And so the KL combinations that give me exactly Q0 amount of output is going to give you this type of shape. So this is Q0 amount of output. If you are sort of evaluating the same set for another level of output, let's call it Q0 prime, well, it's going to give you this level, but here the relationship between Q0 and Q0 prime is the following. The higher output level means higher level curve, or a level curve that is further away or farther away from the 0 point, the origin. So if you are drawing an isoquant, let's call this Q0 double prime. Well, what is the relationship between Q0 double prime with the other two? Well, basically, it's the lowest amount of output. So therefore, as you get closer to the origin, it means a lower level of output. As you move farther from the origin, it means higher output levels. Well, is it always true? It is always true if the production function is an increasing function. All right, for example, the Cobb-Douglas production function. Well, we are later going to use, for example, if the production function is what we call Leontief, so minimum of A capital B labor, where A and B are some positive real numbers. Well, this time the shape is going to be very much like the indifference curve's L shape, all right? So if this is, again, my K versus L graph, this is going to be, so all those isoquants will be moving on an array, which is AK equals BL straight line. All right, so when A is equal to B, for example, this is going to be 45-degree line. And then they all have an L shape, but the king point is always on this AK equals BL line. All right, and once again, this is an increasing function. So as those level curves moves farther from the origin, it means higher levels of outputs. Well, can we give an example where this is not really the case? I mean, I know it's a very sort of a weird example, but f of KL equals to minus x times y, all right? Well, first off, what does minus really means? I mean, you can't really produce minus amounts of outputs, right? I mean, what does that mean? If you like, if you want to make it a bit more realistic, you can assume 100 minus xy, okay? So some, constant minus xy. So basically, as you use more input, right? So higher x, higher y, it will reduce your production. So this is not an increasing function. So therefore, if you calculate the level curves for this production function, well, this time, the level curves that are farther from the origin are not do not represent higher levels of output. Just the opposite, level curves that are closer to the origin actually represents higher levels of outputs. Okay? Is this a realistic production function? That's totally another subject. But most of the times it's not, because as I said, our general assumption is that the marginal productivity of capital or the marginal productivity of labor, we assume that they're positive. So therefore, the production function is actually increasing function. And the diminishing marginal productivity, remember the assumption, the second derivative is negative. Okay, so I am skipping all these rather faster, maybe, because almost all these notions are actually sort of familiar to us from the utility theory or the demand theory. Well, if you remember, we had the indifference curves, and then we talked about the slope of an indifference curve, right? So here we're going to talk about slope of an isoquant. So what is a slope of an isoquant? Well, mathematically it is basically a minus. That's because of the diminishing marginal productivity, or sort of a downward sloping. These are all downward sloping curves. It's minus del F, del K, del F, del L. Or it's minus marginal productivity of capital divided by marginal productivity of labor. And there's a special name for this. We call it MRTS. So it's basically marginal rate of technical substitution. Okay, so how much units of capital I need to replace for the units of labors just to keep my production level the same. All right, that's the idea. So on one isoquant, I would like to keep my production level Q0 prime, let's say, and so I am here, I'm using this much capital, this much labor, and so I would like to move slightly to this side, meaning I would like to use less capital, maybe because capital is too expensive. But the thing is, I don't want to produce less, I want to produce exactly the same amount of output. And so I would like to come back to this curve. And so I am using less capital, but I need to use more labor. So the question is, what is the ratio between this capital and this labor? Well, obviously here, because the change here is big, right? I mean, this is not, this is several units of capital, this is several units of labor. And so it's just a triangle, and I am trying to find the sort of the slope of it. But the thing is, if I do this change in a very, very small amounts, all right, not sort of 1 or 2 units, but infinitesimal unit. And so it basically means this is the slope. I am actually looking at a slope of a tangency line at this point, all right? So this is the tangency line. So it's a tangent to my isoquant curve at this point. So the question is, if I want to change my capitals slightly, how much slight additional units of labor I need to use just to keep my level of production the same. So that's the idea of marginal rate of technical substitution. As I said, it's the slope of the isoquant curve. So I am not explaining how we calculate this, but remember, we can calculate this by taking the total derivative of the isoquant curve, right? Meaning when you have Q0 equals f of KL, so Q0 is a constant. So when you take the derivative of both sides, the derivative of this side is going to be 0. And so I'm going to be taking the derivative of the production function, and so total derivative of the production function. And so I can write the slope of this tangency line as such. All right? So we already did this in the utility theory or the consumer theory, and so I'm going to skip this.